So this video is on second order derivatives. Now I want to start this video with talking about stationary points. Now up to this point you might know these as turning points. You can call them that still if you want, but this is kind of more of a correct term. So a stationary point is basically when a curve turns around, which is why they're also called turning points as well. And you've met these already in chapter 2 with quadratics and chapter 4 with cubics and quartics. So for example, here we have a generic quadratic graph, and the turning point is here. It's the point where the kind of graph turns. And we have a generic cubic here, and it has two stationary points. It has one here, and it has one here. And the key feature of stationary points is that they exist when the derivative is equal to 0. And this makes sense if you think about it, because this is where the gradient is 0, because you can see at these points, if you draw a tangent if you want to, you can see at these points this is where it is flat and it has a gradient of 0. So a question could ask you to find the coordinates of all the stationary points in a graph. So they've given this graph here and they want us to find the coordinates of the stationary points. So as we just said, this is going to be when dy over dx is equal to 0, and therefore what we do is we find dy over dx of this, equal it to 0, and then find the x coordinates for what this is. So first of all, let's find dy over dx. So dy over dx is going to be equal to, so first of all let's write this in a bit more of an easy to integrate form. Let's do y is equal to x plus, and then it's x to the power of minus 1, and therefore dy of dx of this is going to be, remember we differentiate the terms individually, so x is going to be dy over dx of that is going to be 1, and then x to the minus 1 is going to be minus x to the power of minus 2. So dy over dx is going to be 1 minus x to the minus 2, and we need to find the x coordinates for when this is equal to 0. I'm going to write this in the fraction form of 1 minus, and then it's going to be x squared under 1 is equal to 0, and then we just solve this. I'm going to move this onto the other side to do 1 is equal to 1 over x squared, and I'm going to put this numerator onto the other side, so it's going to be 1 divided by 1, which is just going to be 1 is equal to x squared. So therefore x is equal to plus or minus the square root of 1, which is of course just 1. Now in the very first differentiation video, I talked about how useful your calculator is for checking the answers for a differentiation, because what you can do is you can put this function into your calculator and then put these x coordinates into your calculator for the x is equal part, and this should give out equals to 0, because dy over dx for these x values is equal to 0. Go back to the first differentiation video if you don't know what I'm talking about, but this is a really powerful way to check that you've got the right answer for the differentiation. And therefore what we can do now is we need to find the coordinates. So all we just do now is sub these x coordinates into y to find the y coordinates. So therefore when x is equal to 1, y is going to be equal to, and then we sub 1 as x into this, so it's going to be 1 plus 1 over 1, which is going to be equal to 2. So one of the coordinates is 1, 2, and then the other coordinate is going to be when x is equal to minus 1, so y is going to be equal to minus 1 plus 1 over minus 1, which is going to be equal to minus 2. So the other coordinate is minus 1, minus 2. So the coordinates of all the stationary points are 1, 2, and minus 1, minus 2. So here's another example of this where we need to find the coordinates of all the stationary points for this graph here. So again, this is going to be where dy over dx is equal to 0. So first of all, let's find dy over dx. And this is going to be equal to, and then we differentiate this, and we differentiate all the terms individually. So 2 over 3, x to the power of 3 is going to be 2 over 3 times, and x to the power of 3 differentiated is 3x squared, which is equal to 2x squared as the denominator cancels out. Half x squared is going to be half times, and an x squared differentiated is going to be 2x, and this is going to be equal to x, and then minus x is just going to be minus 1, as when you differentiate an x term, the x just goes away and the coefficient stays, and then the constant at the end when you differentiate goes away. So dy over dx is equal to, and then these terms added together, 2x squared plus x minus 1, and we need to find when this is equal to 0, and this is just a quadratic equation. There's loads of ways that we can solve this, as we talked about in chapter 2. I'm just going to do it by factorising. So this is going to be 2x, and then this is going to be x equal to 0, and then eventually you'll find that this is going to be plus 1 and this is going to be minus 1, because this will give the plus x in the middle. So therefore x is going to be equal to a half and minus 1. So these are the two x values, and again you can check your answer by putting this function into your calculator and then putting in a half and minus 1 in as the equal to x values, and this should give out equals to 0. So this is a really good way to check your answer, and therefore to find the coordinates we just need to find y, and therefore we just sub the x coordinate into this. So when x is equal to a half, y is equal to 2 over 3 half cubed plus a half and then a half squared minus a half plus 6, and if you put this into your calculator, this is equal to 137 over 24. So one of the coordinates is a half and then 137 over 24, and then the other coordinate is going to be when x is equal to minus 1. So this is going to be when y is equal to 2 over 3 minus 1 cubed plus a half minus 1 squared minus, and then it's going to be minus 1 plus 6, and if you put this into your calculator, this is equal to 41 over 6. So the other coordinate is minus 1, 41 over 6. So the two coordinates of the stationary points are a half and 137 over 24, and minus 1 and 41 over 6. So now let's discuss second order derivatives, and these are really easy. These are just the derivative of the derivative. So let's do an example. Let's say that y is equal to x to the power of 3. So dy over dx is going to be equal to 3x squared. And then the second derivative is we just differentiate this again. And we write this as d squared y over dx squared. Remember, this is kind of weird that the 2 is here for the numerator and the 2 is here for the denominator, which is going to be something you're going to have to remember. So the second order derivative is literally just this differentiated again. So it's going to be 3 times, and the derivative of x squared is 2x, which is equal to 6x. So d squared y over dx squared is equal to 6x. Now, if it was written instead as f of x, we know that the derivative of that is f dash of x, and if we derive that again, that will be f dash dash of x. So we would just write it like that. So again, this is really, really simple. It's just more differentiation. So here's a few examples. So y is equal to root x, which we can of course write as y is equal to x to the half. So dy over dx is going to be equal to a half x to the power of minus a half. So therefore, the second derivative, d squared y over dx squared, is going to be equal to a half times, and then this differentiator, which is going to be minus a half x to the power of minus 3 over 2, which if you simplify is equal to minus a quarter x to the power of minus 3 over 2. The second example, f of x is equal to 3 over 2 x squared. So f dash of x is going to be equal to 3 over 2 times, and it's going to be 2x, which is just going to be equal to 3x, and therefore f dash dash of x is just going to be equal to 3. And then the third example, y is equal to 2 over x, so y is equal to 2x to the minus 1. So dy over dx is going to be equal to 2 times, and then x to the minus 1 differentiated is minus x to the minus 2. So this is going to be minus 2 x to the minus 2, and therefore d squared y over dx squared is equal to minus 2 times, and it's going to be minus 2 x to the power of minus 3, which is equal to 4x to the minus 3. So what is the second order derivative? So in actual terms, it's the rate of change of the gradient. So it's actually the rate of change of the rate of change, but the main use of it is determining the type of stationary points. So there are 3 types of stationary points. The first type is called a local minimum. and this will be here. And this is where it goes from a negative gradient to a positive gradient. The second type is called a local maximum, and this would be here, and this is where it goes from a positive gradient to a negative gradient. Now really quick, the reason these are called local maximums and local minimums is, let's say we have a cubic like this. This here would be a local minimum, but you can see this isn't actually the minimum of the whole graph, because we have obviously these points that goes all the way down here. But in this area, this is the minimum, so it's called the local minimum. And the third type of stationary point is called a point of inflection. And this would be a point like this here, and this is where it goes from a positive gradient, and it goes through a stationary point, but it remains a positive gradient. It could of course also be the opposite, where it's like this, there's a point there, and it goes from a negative gradient and it stays as a negative gradient. Now you can see that these are all stationary points, because for all of them f dash of x is equal to 0. The gradient is 0 at all the points that are circled. The gradient is 0 here, the gradient is 0 here, and the gradient is 0 here. And they're all types of stationary points. So how can the second order derivative help us determine which is which? Well, let's say we find an x coordinate where f dash of x is equal to 0. So we know it's a stationary point, but we don't know which of the local minimum, local maximum, or point of inflection it is without looking at a graph. Well, if f of dash dash of x is bigger than 0, it's a local minimum. And if f dash dash of x is less than 0, it's a local maximum. Point of inflections we'll look at it in a sec, because they can be a bit weird, but second derivatives are really useful because they'll be able to help us determine whether a stationary point is a local minimum or a local maximum. So here's an example question where you need to find the coordinates of the stationary points and then find the identities of what type of stationary point they are. So for part A, we need to find the coordinates of all the stationary points. So this is when f dash of x is equal to 0. So f dash of x is equal to, and we differentiate these terms individually, so x squared is equal to 2x, and then it's going to be minus a quarter times, and x to the power of 4 is 4x to the power of 3, which the denominator is going to cancel out to give minus x cubed, then the constant just goes away. So therefore f dash of x is going to be equal to 2x minus x cubed. And we need to find the values of x for when this is equal to 0. So we can factor out the x to do x of 2 minus x squared is equal to 0, and we can solve from here, because remember, the only way this can be solved is if one of these is equal to 0, because 0 times something is equal to 0. So this is when either x is equal to 0 or when 2 minus x squared is equal to 0. So x squared is equal to 2, so x is equal to plus or minus the square root of 2. So x is equal to 0 and x is equal to plus or minus the square root of 2. So there are 3 coordinates. Now you can check this again using your calculator by using the d over dx function and putting this function in, and then you can put 0 plus root 2 and minus root 2 in, and this should give out 0. And that's a really good way to check if you've got the right answer. And we can find the coordinates from here easily by just subbing in these values into the equation to find the y coordinate. So f of 0 is equal to 0 squared minus a quarter, 0 to the power of 4 plus 2, which is just going to be 2. F of root 2 is going to be equal to root 2 squared minus a quarter of root 2 to the power of 4 plus 2, which is going to be equal to, so this is going to be 2 minus a quarter, 4 plus 2, which is going to be equal to 2 minus 1 plus 2, which is going to be equal to 3. So that means that this coordinate is going to be root 2, 3, and this coordinate is going to be 0, 2. And then f of minus root 2 is equal to minus root 2 squared minus a quarter minus root 2 to the power of 4 plus 2, which is also just going to be equal to 3 because you've got 2 and 4 as the powers. And whenever you do a positive or a minus of the same number to the power of 2 and power of 4, it's just going to be the same number. So therefore the other coordinate is going to be minus root 2, 3. And that's the final answer. The three coordinates of the stationary points are 0, 2, root 2, 3, and minus root 2, 3. So for part B, we need to determine the identities of each stationary point as either a local maximum or a local minimum. I've specifically picked an example where there's not going to be a point of inflection, so you don't need to worry about that. So the key to this is doing a second derivative. So the second derivative, or second order derivative, is going to be equal to, and then we differentiate these terms individually. 2x is going to be 2, and minus x cubed is going to be minus 3x squared. So f dash dash of x is equal to 2 minus 3x squared. And then what we do is we sub in each of these x coordinates, and then remember how it works. If f dash dash of x is bigger than 0, then it's a local minimum. And if f dash dash of x is less than 0, then it's a local maximum. So f dash dash of 0 is going to be equal to 2 minus 3 0 squared, which is going to be equal to 2, which is bigger than 0. So therefore, as it's bigger than 0, it's going to be a local minimum. F dash dash of root 2 is going to be equal to 2 minus 3 root 2 squared, which is equal to 2 minus 3, 2, which is equal to 2 minus 6, which is equal to minus 4, and this is less than 0. So as it's less than 0, it's going to be a local maximum. And then f dash dash of minus root 2 is going to be equal to 2 minus 3 minus root 2 squared, and because it's a squared, the positive and negative is affected the same, so this is also going to be minus 4, which is less than 0, so it is also going to be a local maximum. So I know this isn't part of the question, but if we needed to sketch the quartic, we can kind of predict what it's going to look like now, with minus 2 being a local maximum, 2 being a local maximum, and 0 being a local minimum, where it's going to look something like this. Here, where we have this here being minus root 2, this is a local maximum. This here being root 2, this is a local maximum, and this here being 0, and this is a local minimum. So let's take a hypothetical example when we have a stationary point, obviously f dash of x is equal to 0, and we calculate f dash dash of x in order to hope that it's a local minimum or local maximum, and hopefully it will give out a value. But f dash dash of x is also equal to 0. So what does this mean? Well, this is actually completely useless. It doesn't narrow it down at all. It could be a local minimum, it could be a local maximum, or it could be a point of inflection. So what do we do from here? Well, there is another technique that you can use to determine the type of stationary point, which is by analysing the points around x. So let's just say hypothetically that x is equal to 5 in all of these situations. So that obviously means that f dash dash of 5 in this example is equal to 0. It doesn't give us any information on what type of stationary point it is. And let's consider the points around 5. Let's consider x is equal to 4.9 and x is equal to 5.1. Obviously they'll be a lot closer in reality to this, but I just kind of want to exaggerate it to make it a bit more clear. And when x is equal to 4.9, for a local minimum, it will have a negative gradient. And when x is equal to 5.1 for a local minimum, it will have a positive gradient. So therefore, using f dash of x, which is the gradient, if f dash of 4.9 is equal to a negative number, and f dash of 5.1 is equal to a positive number, therefore it's a local minimum. For a local maximum, it will be the opposite. If f dash of 4.9 is a positive number and f dash of 5.1 is a negative number, therefore it will be a local maximum due to the way that the gradients work. And then for a point of inflection, if f of 4.9 is equal to a positive number and f of 5.1 is equal to a positive number, therefore it will be a point of inflection. And of course, we talked before that it could also be a negative gradient afterwards. So therefore, it could also be, or vice versa, where it's either they're both negative. So that works as well. So just to note, this method also works regardless of whether f dash dash of x is equal to 0. So if you prefer this method of analysing the points around 5, you can do it instead of the second derivative if you want. But if f dash dash of x is equal to 0, we have no choice. We have to use this method. So here's an example of a question like this, where we have to find the coordinates of the stationary point and then determine if the stationary point is a local maximum, local minimum, or a point of inflection. So for part A, we have to find the coordinate of the stationary point. It says stationary point and not plural, so we actually know there's only going to be one stationary point. So remember, this is when f dash of x is equal to 0. So f dash of x is equal to, and then we differentiate the terms individually, it's going to be 3x squared and then minus 9 times x squared is 2x, so it's going to be minus 18x, and then it's just going to be 27, and then the minus 27 on the end goes away. So f dash of x is equal to 3x squared minus 18x plus 27, and we need to find when this is equal to 0. First thing I'm going to do is just divide everything by 3, so it's going to be x squared minus 6x plus 9 is equal to 0, and then we can factorise this, and we can actually see that it's going to both be minus 3. So we can actually write this as x minus 3 squared is equal to 0. So therefore, x is just equal to 3, which makes sense because it says there's only one stationary point. It gives us a clue in the question. And therefore, all we just need to do from here is then sub this into the formula in order to get the y coordinate. So f of 3 is equal to 3 cubed minus 9 3 squared plus 27 3 minus 27, and if you put this into a calculator, this is actually equal to 0. So the coordinates of the stationary point are 3, 0. So for part B, we need to determine if it's a local maximum, a local minimum, or a point of inflection. So I always prefer the second derivative method first, so I would do that. So f dash dash of x is equal to, and we differentiate the terms individually, so it's going to be 3 times then x squared is 2x differentiated, so it's 6x, and minus 18 will just be minus 18, and 27 will just be differentiated out. So f dash dash of x is equal to 6x minus 18. And f dash dash of 3, the coordinate that we got, is equal to 6, 3 minus 18, which is equal to 0. So it's the situation we talked about. We have to use the alternate method instead by analysing the points around 3. So 3, so I'm going to use 2.9 and 3.1, and we plug these into f dash of x, not f dash dash of x. We need the gradient, so just f dash of x, and see if these give out positive or negative numbers. So f dash of 2.9 is equal to 3 2.9 squared minus 18 of 2.9 plus 27 is equal to 0.03, which is a positive number. And f dash 3.1 is equal to 3 of 3.1 squared minus 18 3.1 plus 27, and if you put that into your calculator, that is also equal to 0.03, which is also a positive number, so therefore it is points of inflection. It's a point of inflection because it's positive on both sides of the gradient. So 3, 0 is a point of inflection. So finally, really quick, they could ask you to sketch a derivative or gradient function of a function such as this one here. They want us to sketch f dash of x, and this is easy. This is just encapsulating all the skills we've learned so far, as well as graph sketching. So first of all, let's find f dash of s. So f dash of x. So f dash of x is going to be, when we differentiate the terms individually, so it's going to be 1 over 3 times, and then x cubed is 3x squared. This is going to be x squared, and then minus 9x is going to be minus 9, and the 1 just goes away. So f dash of x is equal to x squared minus 9. So we need to sketch this graph. Well, firstly, it's going to be a positive graph, a positive quadratic, because the coefficient of x squared is positive, and the y-intercept is going to be equal to minus 9, because this is the number here. And hopefully you can realize that this is a difference of two squares. It's x minus 3 and x plus 3, because this is a square number here, so we can tell. And if we equal this to 0, we can see that x is equal to 3 and minus 3, so the roots are equal to minus 3 and 3. So we know it's a positive graph, we know the y-intercept, and we know the roots. So we can sketch the graph now. I say minus 9 is about here, minus 3 is about here, and 3 is about here. So we can sketch the graph. So it goes up to there, and then it goes like that, there, and we need to label, remember that this is 3, this is minus 3, and this is minus 9. So this is f dash of x, and that's the final answer. Now, a sketch of the gradient function can be used to see things about a graph easier. So here's the previous question where we've got the curve y is equal to f of x, and then we've got the gradient function that we sketched, y is equal to f dash of x. So firstly, you can use it to identify when a graph is increasing or decreasing. So remember that a graph is increasing if it's got a positive gradient, and decreasing if it's got a negative gradient. So remember that this actually represents how the gradient changes. So if it's above the x-axis, it's got a positive gradient, and therefore it's increasing. And then if it's below the x-axis, it's got a negative gradient, so therefore it's decreasing. And we can see this in the y is equal to f of x as well. It's increasing up to this point where it's got a positive gradient up to minus 3. That's the case here. It's got a positive gradient up to minus 3. And then it's decreasing between minus 3 and 3. And we see that here because it's below the x-axis for these points, minus 3 and 3. And then it increases after 3, and we can see that again here where it's a positive gradient after 3. It can also be used to identify where the stationary points are. So remember, a stationary point is when f dash of x is equal to 0. So this is going to be when y is equal to 0, so it's going to be these points here. This is where the stationary points are, and this is reflected above as well. This is where it's minus 3 and 3, and this is the case here as well. This is where it's minus 3 and 3. So here's a question on second order derivatives. So pause the video, have a go, and I'll go through the answers in about 5 seconds. So for part A, this is just differentiation. So we need to find f dash of x, and this is going to be, so 3x to the power of 4 is, because remember we differentiate each term individually, it's going to be 3 times then x to the power of 4 is 4x to the power of 3, which is going to be equal to 12x to the power of 3. Minus 16x to the power of 3 is going to be minus 16 times then x to the power of 3 is 3x to the power of 2, which is going to be equal to minus 48x to the power of 2. Minus 6x to the power of 2 is going to be minus 6 times, and it's going to be 2x, which is going to be minus 12x, and then 48x is just going to be 48. So therefore f dash of x is going to be 12x cubed minus 48x squared minus 12x plus 48. And again, you can use your calculator to check this by putting this function into your calculator, making x equal to something, and then subbing that value of x into here and seeing if you get the same value out. So for part B, it tells us that f dash of minus 1 is equal to 0, and then it wants us to fully factorise f dash of x. So what this is factor theorem, because if f dash of minus 1 is equal to 0, therefore x plus 1 is a factor of f dash of x. Go back to the chapter 7 videos about factor theorem if you don't recall that. But from that, therefore, we can do algebraic division of x plus 1 dividing f dash of x. And this should give a quadratic with no remainder, so it should just be a clean quadratic, and therefore we can factorise from there a lot easier the quadratic rather than the cubic. So algebraic division again was chapter 7, so again go back to that if you don't remember it. But basically this is going to be 12x squared, and then it's going to be minus 12x cubed plus 12x squared. And then these two will just cancel out, of course, and then it will be minus 48x minus x squared minus 12x squared, which is going to be minus 60x squared. And then bring this down. This will be minus 60x, and then minus, and then it's going to be minus 60x squared minus 60x, which is going to be equal to, again, these two cancel out, and then it's going to be minus 12x, and it's going to be minus so plus 60x, which is going to be equal to 48 x, and this is plus 48, and then this will be plus 48. Again, we can check our answer by doing this again and minusing 48x, and it'll be plus 48, and this does give a remainder of 0, so therefore we know that we've done it right, and it gives a clean divide. So therefore this is the quadratic which we get, so therefore we can write f dash of x as the bracket x plus 1, and then the quadratic 12x squared minus 60x plus 48. And then we can factorise this quadratic. Firstly, I'm going to take out 12 because all of these terms are divisible by 12. So I put 12 at the front, 12x plus 1, and then this will become x squared minus 5x plus 4, and there we can therefore we can factorise this to become 12 x plus 1, and this is going to become, we need to times by this and add to get to this, and this will be x minus 4 and x minus 1. So this is f dash of x fully factorised. So for part C, we need to find the coordinates of the stationary points. Remember, the stationary points are where f dash of x is equal to 0. So this is going to be when this whole thing here, 12 of x plus 1, x minus 4, x minus 1 is equal to 0, and therefore each of the brackets is going to equal to 0, so therefore x is going to equal minus 1, 4, and then 1. And then what we can just do is then sub these into here in order to get the y coordinates for the stationary points. So f of minus 1 is going to be 3 minus 1 to the power of 4 minus 16 minus 1 to the power of 3 minus 6 minus 1 squared plus 48 to the minus 1, and this is going to be equal to minus 35. So one of the coordinates is minus 1 minus 35. F of 4 is equal to 3, 4 to the power of 4 minus 16, 4 to the power of 3 minus 6, 4 to the power of 2 plus 48, 4, which if you put this into a calculator is equal to minus 160. Therefore another coordinate is 4 and minus 160. And then finally, f of 1 is equal to 3, 1 to the power of 4 minus 16, 1 to the power of 3 minus 6, 1 squared plus 48, 1, which again, if you put into a calculator, is equal to 29. So the final stationary point is 1, 29, and those are the 4 stationary points. Now again, you can check if these x points are right by again using the d over dx function in your calculator, putting in this original function in, then put in minus 1, 4 and 1 in, and they all should give out 0. So that's a good way to check that you've got the answer right up to this point. So for part D, we need to determine if each stationary point is either a local minimum, local maximum, or point of inflection. Now you could do this by analysing the points around x, but I'm going to do it by the second order derivative, which is equal to, we do each of the terms individually, so 12x from f dash of x here, so 12x cubed is going to be 12 times 3x squared, which is equal to 36 x squared, minus 48 x squared is going to be minus 48 times 2x, which is equal to minus 96 x, and then minus 12x is going to be equal to minus 12, and then the 48 just goes away, so therefore f dash dash of x is equal to 36 x squared minus 96 x minus 12, and then we just sub in all the values and see if they're positive or negative, or of course 0. So f dash dash of minus 1 is equal to 36 minus 1 squared minus 96 minus 1 minus 12, which if you put it to a calculator is equal to 120, which is a positive number, so therefore this is a local minimum. Then f dash dash of 4 is equal to 36 4 squared minus 96 4 minus 12, which is equal to 180 if you put it into a calculator, which is again positive, so this is also a local minimum. And then for the f dash dash of 1, it's equal to 36 1 squared minus 96 1 minus 12, which is equal to minus 72, which is a negative number, so therefore this is a local maximum. So for part E, we need to sketch f dash of x. Be careful with f dash of x and f of x. This is what we're sketching. So we need to know whether it's a positive or negative graph. We need to know the roots, and we need to know whether it's a y-intercept. Coefficient of x to the power of 3 is positive, so therefore it's going to be a positive graph, and we know how that looks from chapter 4. The y-intercept is going to be 48. So that's the number on the end. And then the roots are going to be when this is equal to 0, which we actually figured out before is going to be minus 1, 4, and 1. So therefore from here we can sketch the graph. We'll say that 4 is about here, 1 is about here, and minus 1 is about here, and we'll just say that 48 is somewhere along here, but it doesn't really matter too much. It's going to be a positive quartic that's going to come up like this, meets here, then it's going to come like that, then come down like that, and then up like this. Remember to label, this is going to be minus 1, this is going to be 1, this is going to be 4, and this is going to be 48. And that's the final answer.